We're going to start looking at the concept of molar mass. I've mentioned it before. Molar mass. Sometimes you'll hear me use the term formula weight. And this is simply how many grams there are in 1 mole of a substance. So, like water, H2O. We've done this before. If I look at H2O, I know there's 2 hydrogens, and I also know that there's a single oxygen. And if you look on your periodic table, I remember at the bottom that tells us the molar mass, or the atomic weight. Of our elements. You'll notice that, and I'm gonna approximate because I don't have the periodic table in front of me, but you should look at it, maybe write down exactly what the numbers are. But hydrogen is basically 1 gram for every mole, and there's 2 of them in water, so I say there's 2 times 1, which is 2. Where this is the atomic weight of hydrogen. And then if we look up oxygen, there's only 1 of them. We know there's 16. Excuse me, there's 1 oxygen atom, and its molar mass, its atomic weight, is 16 grams in a mole. So if we just, add everything up, because those are the pieces that make up water, we get 18. And that's going to be 18 grams per mole. That's going to be the mass of 1 mole of water. We might also call it the formula weight. We wouldn't call it the atomic weight for water because water is not an atom, it's a molecule. So you could call it the molecular weight. You might see that as well. What's interesting about this is we can think about molecules in some different ways. We can think of the ratio of atoms in water, and if we think of the ratio of atoms in water, we see that there's 2 hydrogen atoms for every 1 oxygen atom. We can also think of the ratio in a molecule or in a compound in terms of mass. There's a mass ratio that exists in water. Let me just show you that here. We know that overall water has a mass of 18 grams for every mole. 2 of those grams per mole come from hydrogen atoms. So I can say 2/18 of the mass of a water molecule comes from hydrogen. If you do the math, it comes out to 0.11, which is about 11%. I think it's 0.1 repeating. Let me just make sure that's right. I think that's right. Doing some math in my head here. 2 divided by 18. Yeah, 0.1 repeating. Then we can do the same thing with oxygen, right? 16 grams of the 18 grams per mole, well, that comes from oxygen. And so we can say 16/18 of the mass of water is going to be oxygen, and that's going to come out to roughly 89%, because it's going to be 88.8. We'll round that up to 89. So there's 2 ways we can think about the relationships that exist between atoms and compounds. We can look at the number ratio, which in the case of water is going to be 2:1, hydrogen to oxygen. We can also look at the mass ratio, which is going to be 11 to 89, hydrogen to oxygen. So although there's more hydrogen atoms in the compound by number, there's more mass in the compound oxygen. There's more oxygen by mass in the compound than hydrogen. And that's very important to keep that distinction in mind. It should make sense, right? If we're looking at a car, what's the mass of, say, steel in that car versus the mass in rubber? Well, the mass of rubber just probably comes from the tires, and that's about it. And that's not going to contribute much to the mass of the overall car. And in the same sort of way, hydrogen, it's a very small, very light atom, and it doesn't contribute much to the mass. In fact, oxygen, each oxygen, let's see, each hydrogen contributes 1 gram per mole. Each oxygen contributes 16 grams per mole. Oxygen is 16 times heavier. So it doesn't take, you'd need 16 hydrogens for every oxygen to have an equal ratio of mass of those two atoms in the compound. So we're going to look on, let's see, I'm on slide number 19 in the PowerPoint that defines molar mass of compounds. And there's 2 listed down below. There's aspirin and there's magnesium hydroxide. And you'll notice for aspirin, the term given is molecular weight because aspirin is made of molecules. So let me write the formula here for aspirin, C9H8O4. This is aspirin, and we would say we can look up the molecular weight for this. And we're going to do that in a second. And then I also see magnesium oxide. Magnesium oxide, it's an ionic compound. How do I know? There's a metal there. If you look on the periodic table, you'll see that magnesium is on the left side of the periodic table. It's a loser to the left. It's a metal. So because of that, I know this is ionic. And you might remember that ionic compounds are not made of molecules. They exist in these array of ions that form this 3-dimensional lattice. There's not individual molecules. So it's inappropriate for me to use the term molecular weight to talk about magnesium oxide. Because of that, we use the term formula weight when talking about ionic compounds. We look at this formula. There's 1 magnesium for every oxygen, and based on that formula, what's the mass in moles of this particular formula. So let's calculate these. Just make sure we know how to do it. So I'm going to look at aspirin, which is C9. So let's see, I have carbon. There's going to be 9 of those. So I'm going to take 9 carbons times, if I look up the atomic weight of carbon, it's 12. It's going to be something else if you actually look up the actual number on the periodic table, but I'm just estimating here. So what's that, 108? Yep. Hydrogen, there's 8 of those times 1 gram per mole each. Hydrogen is going to contribute 8 grams per mole to the total. And then we have oxygen. Well, there's 4 of those, and that's 16 grams per mole. That's going to be 64. Let's add all that up. 8 and 8 is 16, and 4 is 20. Carry the 2. I'm getting 180. If I did my math right, that tells me that the molecular weight of aspirin is 180 grams for every mole of aspirin. And once again, we can do the percent by weight calculation. It's very easy to do, right? To find the percent by mass or percent by weight of carbon in aspirin, I just take 108 and divide it by 180. To find the percent by mass of hydrogen in the compound, I just take 8 and divide it by 180. And to find the percent by mass of oxygen in the compound, I just take 64 and divide that by 180. And what's interesting about this is it actually gives us a way to take a compound that we don't know the formula for, and if we analyze that compound and we find the percent by mass of each element in the compound, we can go from the percents to the formula. And we'll do that in a little bit. First, I want to calculate the molar mass of magnesium oxide. Sorry, I said molar mass. I should have said formula weight. I guess molar mass is appropriate too, because that would be the mass of 1 mole of magnesium oxide. So that would be okay. It wouldn't be appropriate for me to say the molecular weight of magnesium oxide. So let's see, I have 1 magnesium. If I look that up on the table, you can see that's 24.3 grams for every mole. I also have 1 oxygen. I looked that up. It's going to be 16 grams per mole. I add everything up, and I get 40.3 grams for every mole of magnesium oxide. So let's go to slide 21 on your PowerPoint. We're going to skip slide number 20. And this is this idea I was talking about, percent composition. The atoms in compounds, if you take a pure compound and you analyze the elements in that compound, you're always going to find the same ratio by weight of the elements to each other. So if I take a sample of water and I analyze that water, it's always going to come out about 89% of the mass in that water is going to be oxygen, and 11% by mass in that compound is going to be hydrogen. If let's look at these. Let's do magnesium oxide. So I'm going to take, let's see, 24.3. I'm going to divide that by 40.3. So if I was going to take a sample of magnesium oxide, we'd always find roughly 24.3 divided by 40.3. That comes out to 60.3%. So every time I analyze some pure magnesium oxide, I'm going to find 60.3% by mass of that compound is going to be magnesium. And what's the remainder? Well, let's just figure it out. Let's see, it'll be 16 divided by 40.3. (39.7%). Of course, we had those up. That better be 100. 39.7% by mass of that compound is going to be oxygen. And it doesn't matter if I have a small sample of magnesium hydroxide or a huge sample of magnesium hydroxide. It should always come out in this ratio by mass. That's by mass. By number, it's 50-50. There's one magnesium for every oxygen. So it's a good idea when you're doing problems in chemistry to keep in mind, do I want to know the mass ratio here, or am I interested in mass, or am I interested in number? And how do mass and number connect to one another? Remember, mass and number with these chemical compounds, they're connected with the molar mass, the grams per mole. You see that? There's your connection. This, for magnesium oxide, this is my connector between mass and number. 40.3 grams is the same thing as 1 mole if I'm talking about magnesium oxide. That's a conversion factor I can write. Okay, so there's some examples on slide 21. We actually did the first one. What is the percent by mass of oxygen in water? We already found that was 89%. Let's try number 2. Why don't you try this? What is the mass percent of hydrogen in the compound CH2O? So your job is to find, there's our molecular formula, and you're supposed to find the percent by mass of hydrogen in CH2O. Why don't you pause the video and we'll come back and see how you did. All right, let's try this. I've got my compound. I want to find the percent by mass of hydrogen in that compound. I have 1 carbon. That's going to be 1 times 12. Where do I get that 12? That's from looking at the periodic table underneath the symbol for carbon. I've got 2 hydrogens. So there's 2 of those. That's 1 gram per mole. I find that information from the periodic table. I've got 1 oxygen. 1 times 16. Again, that 16 comes from the periodic table. I got to add all these up. 12, 2, and 16. That looks like 10. If I did my math right, it looks like the molar mass of this compound is 30 grams for every mole. Now I can just take my hydrogen. Hydrogen totally, there's 2 of them, contributes 2 grams to the 30. And so it's going to be 2/30ths. 1/15. What is that? About 6%. 1 divided by 15. Yep. 6.7%. It's approximate, of course, because I'm rounding. That's going to be 6.7% by mass of hydrogen in this particular compound. Even though it's half of all the atoms, right? I have 4 atoms total in this thing. 2 of them are hydrogen, one's carbon, one's oxygen. By number, hydrogen is 50% of the atoms in the molecule, but by mass it only makes up 6%, or 7% roughly. Okay, now let's do number 3. This one we're going to work backwards. So in this case, we're going to analyze a compound, glucose, it's blood sugar, and if glucose is analyzed, there's different methods for doing this. We're not going to worry about that right now. But we could analyze glucose and we could find that 40.0% of glucose is carbon. We also find that 6.7% of glucose is hydrogen. And we also find that 53.3% of glucose is oxygen. From this information, we can find the lowest ratio of carbon to hydrogen to oxygen in glucose. We can then use that information and the information from a second experiment. I know that glucose is 180 grams for every mole. So given that this is the molecular weight of glucose and this information, we're supposed to find the molecular formula for glucose. That's our task. So here's the simplest way to do this. We just imagine we have 100 grams of glucose. We could do this, we could imagine we have a gram. A gram of glucose is going to have this ratio, percentage-wise. 100 grams of glucose is going to have this ratio in percentages of carbon to hydrogen to oxygen. A kilogram of glucose is going to have this ratio. So it doesn't matter what we choose. All glucose, all samples of glucose, if they're pure, have this ratio of carbon to hydrogen to oxygen. It just makes mass easy if you say, well, let's pretend we have 100 grams of it. Because if I do, then I know I have 40 grams of carbon, 6.7 grams of hydrogen, and 53.3 grams of oxygen. Why don't we just do that? That's going to make it easy on ourselves. So if I imagine that, because what I'm trying to do here, I'm trying to get to the numerical formula for glucose. So I'm given mass, and I'm trying to go to the number ratio of atoms in the compound. That's where we're going. So let's see, I've got 40 grams of carbon, and I've got 6.7 grams of hydrogen, and I've got 53.3 grams of oxygen. And my question for you is, how do I convert these masses into a number? This is the mole idea. Remember, we can always look at the periodic table, and underneath the symbol, we have a connection between mass and number, between grams and moles. So what I'm going to do here is I'm going to convert all these to moles. When you convert to moles, you've converted to a number. Just like if I convert something from some units to a dozen. A dozen's a number. A mole's a number. So let's go ahead and convert this to moles. If I look on the periodic table underneath carbon, you're going to see 12 something. We're just going to say 12 grams for every mole of carbon. So if I do this, well, that's going to be grams of carbon. So this is going to cancel this. 40 divided by 12, that'll tell me my moles of carbon. What's that going to be here? 40 divided by 12, 3.33 moles of carbon. Well, hydrogen's always easy. It's 1 gram per mole. 1 gram of hydrogen is 1 mole. So for hydrogen, no other compound, the grams and the moles are the same. Pretty much. I mean, this is a little off one, but for the most part. So let's see, that's 6.7 moles of hydrogen. Now I want to convert oxygen, 53.3 grams of oxygen, to moles of oxygen. If I look at oxygen on the periodic table, I look beneath its symbol, I'm going to see 16.0 grams of oxygen. That's 1 mole of oxygen. Notice you might see something different on your periodic table. I'm just doing it from memory, so I don't have all the digits memorized, but I do have a lot of the numbers. Okay, so we're going to go 53.3 divided by 16. 3.33. That's going to be moles of oxygen. So at this point, I could write the following. I'd say, you know, in glucose, which has carbon, and it has hydrogen, and it has oxygen in it, it would be appropriate for me to say there are 3.33 moles of carbon to every 6.7 moles of hydrogen to every 3.33 moles of oxygen. That's an appropriate ratio to write based on the calculations that we've done. But of course, in molecules, you know, atoms don't exist. You can't have a third of an atom. You can't have 0.7 of an atom. We want to talk about whole numbers. So let's think about this. What whole number ratio relationship exists between 3.33 carbons and 3.33 oxygens? Well, that's 1 to 1. And what ratio exists between 6.7 and 3.33? Well, that's pretty close to 6.66. So it's like a 1 to 2 to 1 relationship. Now, sometimes it's not always this obvious. And so what we do when it's not obvious, we divide everything by the lowest number that we see, which would be 3.33. And if we do that, we'll get 1 carbon. What would that be if we got that for, let's just see, 6.7 divided by 3.33. Get like 2.01. Well, that's essentially 1 to 2 to 1 is what it is. And so this is what we would say is the ratio of carbon to hydrogen to oxygen in glucose. So we're almost there. We're not completely there, though, because we're not sure if this ratio that we're given, which is called the empirical ratio, this is the ratio we find when we do this math. We sometimes call it the empirical formula. You can call it empirical ratio. This is what we find from the empirical measurements that we make. But is this actually the number of atoms in a molecule of glucose? Well, that's where this other piece of information comes in. This other piece of information you might remember was we did some experiments with glucose and we found its molar mass is 180 grams per mole. That's the molecular weight. 180 grams per mole. Well, let's imagine this is the molecule. Okay? Let's imagine it. If we did that, we'd say, okay, I got a carbon, I've got 2 hydrogens, and I've got an oxygen. It's going to be 1 times 12. This is going to be 2 times 1, and this is going to be 1 times 16. Let's see, this comes out 12, 2, and 16. If I add that up, I get 30 grams per mole. Well, that doesn't make sense. If this is my molecule, the molar mass of that molecule is only 30 grams per mole. But when we actually do an experiment to see, we find that the molar mass of glucose is 180 grams per mole. It's 6 times this number. That should give you clues what we should be doing. If this is 6 times this, then I need to multiply this by 6. All of these need to get multiplied by 6. The empirical formula needs to get multiplied by 6 to give me the actual number of molecules, actual number of atoms in the molecule. So that would be, what's that? 1 times 6 is 6. 2 times 6 is 12. 1 times 6 is 6. So the molecular formula for glucose is C6H12O6. You might remember that from your biology class in high school. So I want to sort of step back and sort of recap this in a way that hopefully will guide you through when you're doing these particular problems. There's some definitions I'd like to give you, and I believe these are on, this is on slide number 22, empirical formula versus molecular formula. the empirical formula which for glucose is CH2O, happens to be the lowest whole number ratio of atoms in a compound. Lowest whole number ratio of atoms in a compound. Whereas the molecular formula this shows you, this is a representation of the actual number of each atom in a molecule. And to get the molecular formula, what you have to do is you take your empirical formula and you're going to multiply that by the molar mass of compound, which we saw before was 180 for glucose, and we're going to divide that by the molar mass of the empirical formula, which we saw was 30. And we saw this when we took 180 and we divided by 30, we got 6. If we take that 6 and multiply it by the empirical formula of glucose, we end up getting the molecular formula for the compound. Just to sort of, throw one more idea out there to see the difference between this. There's a compound called hydrogen peroxide, H2O2. And I've written on the board the molecular formula for hydrogen peroxide. What would the empirical formula for hydrogen peroxide be? I hope you see that that's going to be 1 to 1, right? The lowest ratio of hydrogen to oxygen is 1 hydrogen for every oxygen. That's the same thing as 2 to 2, but we want the lowest ratio expression of that. So the empirical formula for hydrogen peroxide would be HO. The molecular formula for hydrogen peroxide is H2O2. That's the end of that.